Hi everyone, welcome back to my YouTube channel. I am Inkit Mishra. I've been teaching for Git Chemical Engineering for last few years. So today I'm going to talk about the membrane separation process or membrane mass transfer process. That is also a newly added topic in Git Chemical Engineering. So every year in last 4 years you will see that question came from this topic. So that's why this topic becomes very important. So let's start with the topic first, and I'll try to cover very fast in very small video, right? Okay, so first when we talk about the separation process, so lots of separation process basically we study in your mass transfer, that is distillation, extraction, absorption, drying and humidification. All of these are separation process, and that is also called as a mass transfer. So when we talk about these things, equilibrium based separation process, so your distillation, absorption, extraction and all of these things are equilibrium based separation process, right? But the extent of separation is detected by equilibrium condition only. So that was the equilibrium based separation process. But when we talk about the rate based separation process, so in the rate based separation process, you will see separation is not going to depend upon the equilibrium. So this is going to depend upon due to the difference in the rate of transport of various species, right? So if let's say two species are there, and if you want to separate these two species, so this depends upon the rate of transport of this species. So here comes to the membrane, right? So in membrane, what will happen? This creates a porous kind of barrier, right? So if I am talking about membrane is having porous barrier. So let's say due to change in temperature, change in pressure, change in concentration or change in delta E, that is voltage, that actually occurs in electrolysis process, so separation will be there, right? So if we see the separation process here in membrane, separation process in membrane, so one will be energy separation process, that is distillation. Let's say energy so separation based on energy, so you can say here is distillation, right? Another can be mass separation process. Then it comes extraction, and again external agent separation process. Or separation based on the external agent, so like membrane here, membrane. So all of these things, obviously distillation and extraction we have studied, but here I am going to talk about only membrane separation. So let's start with the membrane separation here. So in membrane separation, generally what you will see, membrane is a phase that will define the rate of transport of the various species, right? So you can define membrane is a phase that will decide the different rate of transport of various species. I'll tell you how we can decide these things. Various rate of transport of various species based on size. Based on size. Okay. So what will happen actually? So membrane size is going to decide which species will transfer and which will not transfer. right? So based on the size of the membrane and the size of the particle. So let's say if I am talking about here, if I am making a membrane something like that, so here you can see the pore size is small, and if I am making a membrane something like that, pore size is large. So here separation will be different, right? Here pore size will be something even, and here pore size is epsilon 2, and you can see epsilon 1 is less than epsilon 2. So in that particular separation from both membrane 1 and membrane 2, you will see that if the separation which is happening here is different from each other, right? So again we'll see all of these membrane separation process, and where which kind of pore size is required, and what kind of parameters are required. So coming to the membrane membranes are made up of polymers, right? So what kind of polymers that can be there? It can be cellulose ester, polyacrylonitrile, and another nitrocellulose membrane is also there. Wattman filter paper that is made up of cellulose. All of these things are there, right? But that is not required here. Now next thing is the hydrophilic membrane. So the membrane which loves water, that is called as hydrophilic membrane, and hydrophilic membrane is used hydrophilic membrane is used when aqueous solution is being filtered, right? So there you can use the hydrophilic membrane. That is very important. Okay? So sometimes in 1 marks they can ask you this kind of question. Now then it comes to the membrane based on the materials. So homogeneous membrane and heterogeneous membrane. So homogeneous membrane will be made of homogeneous polymer, and the heterogeneous membrane made up of two different kind of polymer, right? So due to the heterogeneous nature, the thickness will get increased, and flow resistance will get increased in homogeneous. That's why so homogeneous membrane is mostly used. So if I am talking about the membrane type, so you can have a homogeneous membrane, and there can be heterogeneous membrane. So in case of homogeneous membrane made up of homogeneous polymer made up of two different kind of polymer. So due to the heterogeneous nature of this membrane, what will happen? The thickness increases, also flow resistance increases. So in order to avoid these things, we don't want these things. That's why homogeneous membrane is preferably used. Right, homogeneous membrane is preferably used. Now next is, it's very important point, types of motion through membrane. Types of motion through membrane, right? So let's try to understand. First is permeation, right? So how this transport thing is happening in membrane, right? So first, what will happen? Dissolution of a species will take place. Once it will get dissolved, after that what will happen? Diffusion will start taking place. And once after diffusion, what will happen? Desorption will start, and where the substance will get completely saturated. So first is dissolution, then diffusion, and then your desorption. So if you talk about these things, so RO and reverse osmosis and nanofiltration, all of these things work on basis of dissolution, diffusion, and desorption, triple D. So first, what will happen? The solute will come and get dissolved. Then, due to the concentration gradient, the diffusion will start taking place, and on the other side, the membrane, what will happen? The desorption will start taking place. So this comes under the permeation, right? After that, there is another process, that is Knudsen diffusion. Knudsen diffusion already I have discussed in your chemical reaction, sorry, in mass transfer, when I was talking about the diffusion. So here what will happen? Mean free path will be greater than pore diameter, and there the Knudsen diffusion will occur, right? So this is for the intermediate pore. Here intermediate pore is going to be dominant. So in first case, permeation, pore size will be less, but here you can say that is intermediate pore size. There will be intermediate pore size, and then it comes to the convection, that is the third part of this. How solute is getting transported. So here you will see there will be larger pore size. So if convection has to happen, then there has to be a larger pore size. So this will come under micro filtration. So we'll see the microfiltration, reverse osmosis, all of these things. But if you will increase the pore size of membrane, the diffusion becomes less dominant than the convection, right? So if pore size is being increased, convection dominant over diffusion, right? So let's say if somewhere you want only a diffusive flux, you don't want convective flux. So in that point or in that particular process, you have to use membrane having pore size less compared to the larger pore size. So if you will start using larger pore size, then definitely it is going to start convection will start taking place, and your diffusive effect will get neglected, right? Okay, so now I will be moving towards the next part of the today's discussion, that is the categorization of membrane separation process. That is very important, and from here get to ask questions. Right. So first I'll be starting with reverse osmosis. I'll try to make the video very short, so that in very small time you will be able to complete the topic. So here you will see that a smallest pore size is required. So here that will be 2 to 10 angstrom, right? And it requires highest pressure. Approximately 25 to 40 atm, right? So but you have to keep this main transport method that already I have discussed is transportation, right? permeation, right? And how permeation happens, that is first dissolution, diffusion, and desorption. That's it. And if you want to separate component, obviously you are using membrane, so molecular weight of the solute to be filtered should be less than 100, right? Molecular weight of solute should be less than 100. And when it comes to the application part, so generally it is used for the small amount of monovalent ion, right? So monovalent ion like sodium plus, calcium minus, so and so forth, something like that. So what we have studied in reverse osmosis, pore size should be very small, and pressure drop should be very high, that is 25 to 40 atm. Main transport method is permeation. Molecular size or molecular weight of the solute that is being transported is less than 100, and this is very much applicable for the solute containing monovalent ion like sodium plus, calcium ion minus, something. Now next separation method by reverse osmosis is nanofiltration. So pore size here, it will lie between 5 to 20 angstrom, right? So in earlier case, in case of reverse osmosis, it was 2 to 10 angstrom. Here it will lie between 5 to 20 angstrom. And pressure drop it requires less compared to delta P. I'll write directly here, that is delta P, which is required here approximately 15 to 25 atm. So if you are increasing the pore size, then pressure drop is getting decreased, right? And if I am talking about nanofiltration, it restricts only (60 to 70% of monovalent ion. So here you can see if pore size you have increased, so definitely monovalent ion having obviously monovalent ion is having a smaller size, so monovalent ion will be getting transported, right? So due to this particular reason, you will see if we compare the this reverse osmosis and nanofiltration for monovalent ion, so reverse osmosis will restrict 99% of the monovalent ion, but here in case of nanofiltration, it is going to restrict only 60 to 70% of your monovalent ion. But the molecular weight of solute that is can be separated here, that will lie between 200 to 800. So in earlier case, you can see that molecular weight of solute that can be filtered should be less than 100, but here it provides a bandwidth of separation of molecular weight of solute between 200 to 800, right? So if I am talking about the application part of this nanofiltration, it is used for separation of dye. Okay, that is all about the nanofiltration. Now I'll be talking third point, the third separation process, that is ultrafiltration. That is UF. Okay, in ultrafiltration, I'll directly write pore size, it will lie between 200 to 1000 angstrom. Again, pore size is larger than reverse osmosis, and the pressure drop that is required here, that is 6 to 8 atm. Pressure drop here is very less, 6 to 8 atm apply. And the molecular weight of solute that can be separated here, that can lie between 1000 to 10,000, 1000 to 10,000. And it can be used, what is the use of these things? Used for protein separation. used for protein separation, right? Now moving towards the last point, that is a microfiltration. So when we talk about microfiltration, so here you will see pore size will be greater than 1000 angstrom and molecular weight of solute can be greater than 10,000, and the pressure drop that can be applied here will lie between 2 to 4 atm. So lowest pressure drop that is applied, and here main transport method, because pore size is very large, you can say main transport method, obviously convection, right? So I have already discussed, if you are increasing the pore size, then convection will be dominating step. So now we have talked about all of this separation process that is used by that is happening due to the membrane. So how to decide the performance of a membrane, that is very important thing. So let's try to understand which parameter will decide the performance of the separation of through membrane. Because let's say if we talk about the distillation, there we have seen the relative volatility decides the factor that if relative volatility is greater than 1 or less than 1 or equal to 1, then whether the distillation is happening or not, that can be the case. But here what kind of parameter that can be used to understand whether the separation is happening good or not. So first I'll be talking about the performance of membrane is assessed by following parameter. So first parameter comes here is selectivity of membrane. So that can be defined as CPI divided by CFI divided by CPJ divided by CFJ, and I and J are two different species. Is that clear? So let's say two different species is I and J, and if it is being separated from membrane, so what you will see that if this membrane is there, so concentration here in the feed is CF, concentration here in permeate is P, and concentration here in reject stream is R. So this is your reject stream, this is permeate stream, and this is feed. So let's say here you have two species I and G. So here you will be calculating the concentration of ith species in P and Cj species in P, and here obviously concentration of ith species in feed, concentration of jth species in F. So if I want to define the selectivity here, so concentration of ith species in feed, permeate divided by concentration of ith species in feed divided by concentration of jth species in feed divided by concentration of jth species in permeate by feed. Is that clear? So this is how you can define the selectivity of a particular species transport while using membrane. Now when we talk about the flux here, generally we talk about the volumetric flux. So selectivity of membrane is expressed on the basis of that is either you can write in terms of retention, or you can write so first I'll be talking about the retention. So now what is retention here? So retention of a species will be CF minus CP divided by CF. So the concentration of a species in feed, concentration of a species in permeate, and concentration of a species in feed. This will give you the concentration of a species in these things retentate. So this one is the retentate or reject stream, and this is the permeate stream, and this one is the feed stream, right? So if this one is the membrane, so it can be also written as 1 minus Cp divided by Cf. That is the retention. This formula is very important. Sometimes they can directly ask you question, what is the retention of this particular species if concentration of species in feed permeate is given to you. Is that clear? and obviously selectivity I have already discussed here. Now coming to the volumetric flux. So this will be denoted as JV, that is equals to minus LP into del P by del X. So LP is the thickness of the membrane. So JV is the volumetric flux, LP is the thickness of membrane, and JV is equals to volumetric flux, and obviously del P by del X is pressure gradient. Pressure gradient, is that clear? So the pressure gradient that I have taught there, that delta P. So let's say we have reverse osmosis, we have nanofiltration, we have ultrafiltration, and we have microfiltration. All of these things already I have discussed. And the pressure drop which is required in all of these process, in reverse osmosis I have told you that will be your 30 to 40 atm, that was the highest. After that was 15 to 25 atm, then it got reduced to 5 to 10 atm, and here this is very less, 2 to 3 atm. So pressure drop required here is highest in RO and lowest in MF, but pore size was highest in these things. If I am talking about pore size, so pore size we have seen that pore size here it was lowest, 5 to 20 angstrom. Here it was 200 to 1000 angstrom. Sorry, pore size here was only 2 to 10 angstrom. Here it was 15 to 5 to 20 angstrom. Next, moving towards the next ultrafiltration, here pore size was 200 to 1000 angstrom, and here it is greater than 1000 angstrom. So this was the distribution of pore size in all of these membrane separation process, that is ultrafiltration, reverse osmosis, nanofiltration, ultrafiltration, and membrane microfiltration. So here they can give you this kind of things for match the column kind of question. So they can form a match the column kind of problem from this particular table, and you can solve these things while using this. Is that clear? Okay, so I'll end this lecture here only. In the next lecture I'll be starting with reverse osmosis and osmosis, and after that this topic will get complete, right? So this is very fundamental topic, not very much deep knowledge is required for the GATE examination. You will be able to solve. Okay, thank you.